I'm going to talk about the last application of the fundamental theorem of line integrals, and this is something that shows up in mechanics, the conservation of energy. So let's just go back to 1D, because I think the situation is slightly clearer. So if we look at 1D, we have Newton's second law. And this says that the acceleration, ma, I'm going to call this x prime prime of t. This is equal to the force. And if it's conservative, then it's the gradient of some potential energy. So for example, for the harmonic oscillator of the spring, u of x is just kx squared over 2. So the point is that the conservative condition, F equals minus gradient u, this actually implies conservation of energy. Hence, we understand now why this funny name, conservative. It corresponds to conservation of energy. So why is energy conserved? So what you do is you multiply by x prime of t and integrate. So on a dimension ground, this makes sense, right? Because the acceleration is x over t squared. We multiply by x over t, and now we integrate in t. So this gives you x squared over t squared. This is v squared. This is kinetic energy. So we'll be getting the right quantities when we do this procedure. So let's do the procedure and see what we get. We get m x prime prime of t times x prime of t. And that's the left-hand side. The right-hand side will be minus u prime of x, x prime of t, which I'm going to write now as du dx times dx dt. So it's actually the time derivative of the potential energy by the chain rule. So now for the left-hand side, this looks to me like m v prime of t, v of t, where v is the velocity. So of course this is just the derivative of v squared over 2. So overall we have a time derivative of 1/2 mv squared minus, plus the potential energy, and this is equal to 0. So in other words, if you integrate, the integral of dE dt is 0, and this shows you that the energy at time t minus the energy at time a is actually equal to 0. In other words, the energy is conserved over time. Okay, so this is the 1D situation. Now, in 3D, we use the multivariate fundamental theorem of calculus, which is just the line integral version. So we again multiply by the velocity and integrate. So the Newton's second law is mass times acceleration is the force, which we assume in the conservative case is minus the gradient of u. So now we multiply. So m r double prime times r prime will be equal to minus gradient u dot dr dt. So as before, you would expect 1/2 mv squared. And it turns out this is the case. This is just by the chain rule. It turns out differentiating this gives you that dot product. And therefore, you would expect something similar. In this case, it turns out this is just our usual du dt. U is a function of r of t. So therefore, if you integrate in t, the integral of d 1/2 mv squared dt will be equal to the integral of minus gradient u dot dr dt. So let me just call this k. So that means the integral of the time derivative of k plus u will be 0. This, of course, is the total energy. So in other words, E at t equals b is E at t equals a. So really, it's a very similar idea, and it's because of this step here, the fact that this is equal to a time derivative of the potential. This is where we'd use the conservative condition. I have to emphasize, this is not true if conservative condition fails. If f is not a gradient, the energy is not conserved. So this is a huge application, and I think the vast majority of physics problems have conservative forces. So this is a very useful application of calculus. Thanks for watching.